for the Seriously seminar. It's a pleasure to introduce today's speaker, Mike Riley. Mike got his, like he said, 3 degrees, bachelor's, master's, PhD from MIT. And in '87, he joined Bell Labs, where he was for a long, long time, then became AT&T Labs and so on. It looked like he'd stay there forever until Google came along and offered him a job without having him move to the partner. So that was why he accepted. So he's now at Google Labs in New York. I've known Mike for a number of years. I met him, I think, in 96, 97, when he was here for a summer workshop. I think it was a great summer workshop. It was a lot of fun. And I think we did good work in the paper after that. It's still highly cited. And one of the better known papers on using hand-labeled data for pronunciation modeling. Mike is also the author, along with Maria Mori and Fernando Pereira, of the AT&T FSM tools, which of course are very widely used for various speech and language tasks, which we use in our lab. And after going to Google, he's created a new, better, improved version of it, along with some colleagues, and we're going to talk about that and other things today. So you Mike,
thanks. Improved, and the one key word here is open. Right? So you guys were grandfathered in to get a copy of the library, but the rest of the world doesn't have anything to use but binaries. So that's actually one of the main motivations here, is getting something that anyone can use. And this is a joint work with a bunch of folks. Some folks at NYU, Cyril and Marier. Marier is joint with Google. And myself, Johan Schalkwyk, and Wojciech Skut, and I hopefully pronounced those right. Okay, so the OpenFst library is a C++ template library, and it's used for constructing, combining, optimizing, and searching weighted finite-state transducers. And our goal was to do something that, on the one hand, was very clean and easy to use. On the other hand, would scale to Google-sized problems. And in fact, in a minute, I'll mention some of the things we're using it for. And it has its origins, as Sanjeev mentioned. Several of us, actually each of us went off. Fernando, Pereira, Maria Mori, and myself went to 3 different institutions. Each of us went off and did our own started to do our own versions of libraries. Fernando at Whizbang, where that went down. And Maria and I were doing our own versions, and we chose to merge them. And what you see is the result of that effort. And it is available on this website, which if you go to, you will see a bunch of documentation and source code you can download. And it's under the Apache license, which is a very liberal license. I think the only requirement is that you say where it came from. Otherwise, you can use it for whatever you want. Okay. Some of the uses for this library right now, and they're growing. I'm getting email from people around the world doing various things with this that I didn't know about. It's used internally. We're using it in Google for our speech recognition and speech synthesis efforts. If you advertisement for one of our projects, there's 1-800-GOOG-411 you can dial, and you can use it for it's free, and you can use it to connect you to. I gave an example at lunch where you call up and ask for Baltimore, Maryland, and you ask for the Baltimore Museum of Art, and at least with my voice, it works perfectly. And that actually is not using FSTs. Actually, it is using FSTs. It's using a Nuance product, but it's switching over to our own, and we're doing all the recognition, and we're going to have a synthesis system as well. All are based around this library. There's an open OCR project being done as a joint effort between University of Kaiserslautern and Google, called Octopus, and that will be using it. Internally, we're using it in parts of our machine translation effort, and my understanding is Bill Byrne at Cambridge is using this now for their effort, and perhaps others. Okay, and furthermore, we're using it internally for various kinds of pattern matching and extraction. For instance, if you type at Google, when was Abraham Lincoln born, you actually get a question answering result, which says, instead of just a snippet with some web page, you'll actually say, Abraham Lincoln, it'll say born, and it'll say a date, and it will say a link to corroborate that. And FSTs were involved in the extraction of various and sundry features of that, is my understanding. Okay, so let me start with, so I have to win. I have an hour? Okay. An overview of FST's definition algorithm. This is mostly, so I have a mixed audience here. I think I have a bunch of people who are, using this stuff all the time with the old AT&T stuff. I also may have some people that's new to this. I want to give an overview both for those who haven't know much about it, Second, I wanted probably more than people have heard before, even if you use it, you don't know some of the details of the algorithms. I thought I'd just, for illustrative purposes, just go into two key algorithms, composition and determinization. And second, it will help lead into the second part, which we'll be talking about the details, sort of things that are new to the OpenFst library and sort of its design, et cetera. And I think that will be useful for people who want to use this, or in this case here, hopefully switch over to it. Okay? So here's a slide I think I've used a million times. This is just a example of what FST is, and this is a trivial example. May date from our workshop days, right? I think it's just showing pronunciations of two words, data and data. And so we have FST is a finite state transducer which has a bunch of states. Okay, these are states. Have initial state indicated here with a double circle, a final state with, a bold-faced circle, final state with double circles. A path is labeled with an input label, an output label, and a weight. So for instance, this path has data along with it. It outputs the word data and has epsilon symbols, meaning free moves, and the weight is 1 plus 0.5, actually this is probably, so it's 1 times 0.5 times 0.3 times 1, okay? And I assume this is all familiar to folks, but I thought I would just start with that simple example. And just to be clear, transducers are very useful in the following sense. I'm sure if you're not familiar with transducers, you're familiar with finite state acceptors, which represent sets of strings. Transducers represent binary relation between strings, right? And in this case, here's the relationship between phonetic sequences and their orthographic representation as a word. So now let me give some definitions, just so I can give a formal definition of an FST and mention, and this will help describe some of the algorithms. First, let's talk about what a path is. We can have a path, essentially some path through an automaton. It has a source state, a destination state, an input labeling, and an output labeling. So what a path is just going to be all the input symbols along the path. We can also talk about sets of paths. We can talk about, for instance, all the paths between two subsets of states, or we can talk about all the paths between two subsets of states which have a certain input labeling, or all the paths between two sets of state with a certain input and output labeling, okay? And given this, we can define a finite state transducer as a 8-tuple of an input alphabet, an output alphabet, a set of states, a set of input states, a set of output states, a set of transitions, edges, arcs, whatever you want to call it, an input weighting function and a final weighting, initial weighting function and a final weighting function, okay? And the weight associated with a particular path is the sum of all, so the weight associated with the transduction between the string x and y is the sum of all paths which are labeled with x on the input and y on the output, and the weight is going to be the initial weight, the sum of all the paths, such that the weight of the initial part of the path times the weight along the path times the final weight, okay? And these operations, times or plus, can be abstracted. Then in say, a simple case where it's representing probabilities, the times operation can be times, and the plus operation is plus, and the 0 of this algebra is 0, and the 1 is 1. But you can have other choices. For instance, just the trivial case, the unweighted case, the Boolean case, you can have just the set 0, 1 labeling paths, and you'll use or and to combine them, and again 0 and 1. You can take the probability weights, and you can map them isomorphically onto the negative logs, right? You can take the negative log and map it onto minus infinity to infinity, and now the operations become times becomes plus, 0 becomes infinity, 1 becomes 0, and plus becomes this thing down here, which is the negative log sum thing. So why would you want to do some of these things? Probabilities are nice to think about, but if you're doing computation, it's better to keep things in the log domain so that long products become more manageable as log sums and don't overflow or underflow. You can take what's called, in speech, we call it the Viterbi approximation, right, which is simply replace this log sum operation by min, which is taking a best path in some cases rather than the sum of all paths, right? That's for some fanciful reason called tropical, I think because some people who first talked about this were in Brazil. And we're in Brazil. That's my understanding. And So not any particular choice of plus or times works. You have to have certain properties, and the exact properties you need is called a semi-ring, which is basically a ring which may lack negation. So you need essentially identity elements. You need to have a plus and a times. Times have to distribute over plus. Associativity has to apply, and a few other operations, okay? So an example that don't usually talk about, which I will talk about because we need it for some implementation issues, is the string semi-ring. This isn't quite it's almost a full semi-ring. So let me mention first what it is. The set now is strings. The times operation is concatenation. The plus operation is longest common prefix. The 1 is epsilon, the free moved. And we add a new element called the infinite word, which has all the right properties to be 0, essentially. And this is almost a semi-ring. What it does, it is not right distributive. If you with longest common prefix, it's only left distributive. You could also have longest common suffix, which will be right distributive and not left distributive, and they're called the left and right string semi-rings. But almost everything works with that. And we'll see this is very important for many algorithms like determinization.
So Mike, the infinity of a string is what? It's something inside that. If you take the least common prefix with any other string.
Yeah, it's the 0. It's the identity element of plus. It's the identity element of plus, and the other property it has to. It's the annihilator of times, meaning that time something is itself, which is another property of the semi-ring. And you can essentially we're completing the set to have this property. Okay, and because it's the free monoid, you can get away with it essentially. So okay. Okay, so now I'm going to just give a quick litany of all the different operations that are in the library. And in some ways, they're similar to many are similar or identical to what's in the AT&T version. And I'm not going to go through a detailed description of all of them, but I will drill down into composition and determinization just because I think it's good to see those once. Okay, so I start with the rational operations, which are so essentially if you use grep or Python regular expressions, they have one-to-one. This union is basically pipe or, right? Concat is concatenation of in regular expressions, and closure is star. Okay, and in terms of automata, they're very trivial. There's called the Thompson construction for generating things from component automata. So union essentially I just mentioned. So for union, you take two transducers to build the union. You add a super initial state, and you just put epsilon transitions to each of the component machines, and now you've got the union. So very easy to do, and concatenation and closure have similar definitions. That's if you essentially destructively modify the machines you have. But something I want to talk a little bit more later is that we also offer the ability to have essentially on-the-fly or lazy computation. And what that means, and I'll go into it more later, is that you can define new FSTs from component FSTs where you actually haven't done any work at construction time. The work is done as you go. One way to say this is that the complexity of non-lazy operations is some function of the number of states and transitions in your component machines, where in lazy implementations, the complexity is a function only of that which you visited. Right? So if you only explore 2 or 3 edges, you only do the work unfolding of that. And you can imagine why this could be useful. Say, let's take speech recognition, where you're doing searching some enormous space, and your graph, you don't want to build the whole search graph. You just want to build the part you look at. Okay, so in some environments we have pruning or other ways to stop, it's a great thing to do. Okay, another set of sort of easy operations are these reversal. Reverses a string, right? And by the way, I'm giving the definitions here in terms of their weights. It's sort of straightforward. Inverse, since each transducer can be thought of as a binary relation, the inverse relation just interchanges the input and output strings, and the implementation in the non-lazy case is trivial. You just invert the labels. I will give an example later of how we implement both the lazy and non-lazy versions in the library. I think that'll be instructive how on-the-fly operations are lazy or dynamic or delayed. Those are all synonyms, believe it or not. In fact, why lazy and dynamic are synonyms, I don't know, but they are. Project takes a transducer and maps it onto its to an acceptor, basically removing, either keeping just the first input label or the output label. Okay, and I'm indicating along here, although I'm going a little fast, whether there are lazy implementations or not in the library. But essentially, wherever it's possible to build a lazy one, we will. Reverse, I wouldn't go so far as to say it's impossible. It's hard to write in a lazy way.
Excuse me, could you have a version where you don't have only 2 sides of the FST, you have one or 2 and then project when you've done?
You could. You're asking for a multi-tape kind of. You could. We don't actually. offer that, and it's sort of, that's another library. Okay? Be a lot harder, I think, in some sense. I think another way to deal with that would be to abstract the notion of the label, so a label could contain an n tuple. Because at any one time, you're probably only operating on pairs. So that'd be one way to do it. And we don't support that now, but we might. Okay, I think that'd be a cleaner way to do it, personally. Okay, now we get to some interesting operations. Composition, intersection, and difference. And they're all actually underlyingly the same algorithm, or at least related algorithms. Composition, since I mentioned that transducers are binary relations, you can talk about the composition of two binary relations. And this is a very natural thing to do. If each transducer represents, say, some model from A to B, and this is a model from B to C, then composing them is building the joint model that combines them, right? Or the cascaded model, if you will. And intersection is just composition restricted to where the input and output labels of each machine are the same. So it's an acceptor rather than a transducer. And difference is from elementary set theory, right? Is just intersection of A and B complement. So you need to have complement as well. But once you have that, you have difference. Okay, and these, there's an inherent lazy algorithm, and we also have the non-lazy implementations. Okay, so let me just briefly give an example of how composition works, and then I have a pseudocode for the algorithm, which I think is worth going through. Okay, so here is, I'm going to compose these two machines, and the way it works is I'm going to say, so just to show an example, let's take a path through here, this path here. So how do we get AC on this output? So this is the inputs, this is the output. So we have A can transduce to B here, and B can transduce to C. Therefore, A transduces to C with weight 0.1 plus 0.3, which is 0.4. Okay? And similarly, A goes to A here with 0.4. A goes to B here with 0.4. So now A goes to B with 0.8. The sum of we're using sum here, the tropical semi-ring. And then the final weights are the sum of the final weights at the end. Okay? Simple example of at least why this is the composition of this. The algorithm is relatively straightforward if you don't have the epsilon transitions. The idea is to create, the output is essentially, the states in the output are pairs of states from the input. All right? The initial states are simply all the initial states, pairing of initial states from the two machines. And the algorithm consists of starting with some queue which only has the initial states in it. We're going to remove items from the queue and do something with them. And what we're going to do is, as we remove...
Is there any way to zoom in? Unfortunately, we don't have the full projector. I don't know if you can. I don't know if you can zoom in your software.
What's the problem? You can't read it?
It's small. Yeah.
It's not going to be easy, I'm afraid.
You could move your body forward.
I could. Well, I already know what it says.
You know the algorithm, right? So
Not everybody does.
you're exempt.
I was worrying that it was my glasses.
Yeah.
People can't see? Is that a problem?
Yeah.
Let's see if I can do something here. Let's see. How's that?
Exactly.
Right, those of us who can't see it have seen it.
My always worry is I'll get myself into a state I can't get out of here, but I guess it's all right. Okay. Is that good enough?
You just inverted.
Right. Can you see this? So you put your pairs of your initial states into the pairs of initial states into the queue, which is S. You take an item out. I didn't say what the Q discipline is. It's basically arbitrary, which means this is where the on the fly is. You can choose how you expand this, right? And then on the fly, you're going to expand it at whatever way you're walking the machine, walking the output. Take an element out of the Q, and you're going to look at the pair. And let's skip all this. Essentially, this is just handling the initial and final states. And what you're going to do is you're going to look, as I sort of did in the example. I'm going to. So now I can have everything on the screen here. I'm going to look for each. For the two states in the output state is a pair of input states, and for each state I'm going to look at the transitions leaving those two states, and I'm going to say, does an output label of one transition match the input label of another transition? And if it does, now I've got something that's going to be in the output, and the output is going to have the destination state of the output is going to be, here we go. So here's what I'm adding. I'm adding this edge or transition. Its source state is going to be the pair of states that we're at. Its destination state is going to be the destination state of those two edges. Its weight is going to be the product of the weights. Its input label is going to come from the first machine, and its output label is going to come from the second machine. Very trivial algorithm, right? And very natural to do on the fly. It gets more interesting if you have epsilon transitions, and I haven't got time to go into that there. Okay, so now let's see if I can get back to where I was. Okay. So, okay, so another set of, and so composition in some sense is the workhorse of the library and is used for everything. So it's very important to get it efficient, and I'll talk some more about some open problems in composition that we're looking at the end.
There were some notes about something being commutative in the slide before the algorithm.
Right, well essentially for composition to work you have to have the semi-ring be commutative. Right? Yeah, it's obvious in the intersection, right? It's less obvious in composition, but it's essentially it's what makes the algorithm work. Otherwise, you could write composition without commutativity, but you simply have to sort of unfold the whole machine and then just do the right. It's what allows you not to have to unfold the machine. Okay. There's a whole set of operations to optimize transducers. This includes, you might have, for instance, composition, for instance. The result of composition can create a lot of dead ends. Or said more beautifully, non-coaccessible. So non-accessible means you can't get there from the start state. Non-coaccessible means you can't get from that state to a final state. And connect will walk a machine and remove those. There's a classic algorithm using a DFS. Epsilon removal will produce an equivalent machine which has no epsilon transitions from one that does. And this is a marriage of the classical epsilon removal from automata theory and shortest path or shortest distance computation. Okay? By the way, when I say equivalent, for all these things where I say produce equivalent means the machine accepts the same, transduces the same input string to the same output string with the same total weight. Okay? There could be different number of paths in the result with the same input label output, but the weights might be moved along the paths differently, but the relation is the same.
And Michael, epsilon in the case of transducers means both labels are epsilon.
You might refer to that, or you might refer to an epsilon input and the output. But in epsilon removal, yes, it means both. Yes. In fact, there are other operations which deal with each side I'll mention. Do some stuff, right? Determinization. And we'll talk a little bit more about determinization. The job of determinization is to, I think we'll go to the next slide for that. And how do I want to do this? Yeah, let's go to the next slide. So here's a non-deterministic machine which has, the property that it has is that, a non-deterministic machine has the property that at some state there are two transitions which have the same labeling. And this is bad because in any search, if you're trying to match A, you have to go more than one way. It's a classical algorithm in the case of regular unweighted acceptors to produce an equivalent machine which is deterministic. For any state, there's only one way to match a given label. And there's generalizations of that to the weighted acceptor and the weighted transducer case, although there are various caveats of when it will actually work. It always works, for instance, in an acyclic case. Once you have a deterministic machine, you can find the minimal machine, which is equivalent to it, which meaning has the fewest states and the fewest transitions, and is deterministic. Okay? And just to give an example of the and I'll talk about the determinization algorithm a little bit as well, because it's also sort of the other really important operation in my view. Why is that? Because composition is what you use to cascade models. Determinization is sort of the key step to make them efficient to use. Because if you have a lot of redundancy, you're hosed. Right. This is what makes speech recognition search work when you take this route, because you could, for instance, if you just compose to a lexicon with a language model, say in speech, and you look at the backoff state in an n-gram model, which after this operation, you might, in a million words, you might have a million ways to go, all sharing 40 phones, only 40 different phones that can go. If you determinize, you'll now have 40 ways to go. So you've gone from a million paths to explore to 40,000 locally. But that effect occurs throughout the network, and it's critical. And you get enormous speed-ups when you determinize. Okay. So the determinization algorithm is also a relatively straightforward algorithm. In composition, the output was pairs of states from the input. In determinization, the output are subsets of states. In the weighted case, actually, for weighted determinization, there's subsets of pairs of states and a residual weight. Okay? And what the point of the residual weight is to carry on the amount of weight you have so far that you have to, the bookkeeping you have to do as you're determinizing. So you start by inserting, and again you have a queue, you insert into your queue pairs of initial states and the initial weight associated with that state. That's your initial subset. Now again, I have to make this big again, don't I? There we go. Is that big enough? More? How's that? I did too. That's bigger. Okay.
What key did you press to make that happen?
Shift plus. This is Linux. Okay. Take a state out of the queue, and now what are we going to do to determinize? We're going to look. So we're looking for non-determinism. So we're going to for every label. This is, by the way, this is restricted to weighted acceptor, if you will, right? So an input label and a weight, a label and a weight. We look for each label, leaving some. For each label associated with some subset we've taken out, we're going to find all those states, all those transitions with that label, leaving that subset in the output. And we're now going to construct the new, since we're determinizing, we only want to put one transition in the output, even though there may be many in the input with that labeling. And we've constructed that, where have we constructed that? Oh, it's off the screen. You made me take it off the screen. No, I didn't. It's right. Where is it? Where am I in queuing? Q. Here it is. Here it is. I'm sorry. Here we're putting it in, right? So here, the source state is here. We've already seen that. We know what that's the state we moved from the queue. This is the label, which we just say we're going over. Now we have to figure out what the weight and the next state is, right? The weight is going to be just the sum of all the weights associated with each of the transitions. That's there, plus the residual weight we've seen so far that's stored in the subset. Okay, so what's the point of this residual? So if we have two transitions with different weights, we're going to summarize that with a single transition which has the sum of those weights. The problem is now we haven't kept track of what belongs on each of the transitions we started with. So we're going to put the difference, what's left over, if you will, on into the subsets as we go on. So that's exactly what's happening here. We summarized all the transitions with that label with the sum, but now we're having to correct in the subsets in the new state we're creating by putting here's that weight that we've put on the transition. We're now going to divide it by the weight that it should have been, and that's what we're going to be put in our subset. Okay, and that's what we're going to carry on. Okay, and so that tells us what the new pair is for that state, and determines what our new state is in the output. Okay? And then the final states in the output are going to be the final states in if there's one or more final states in if there's a final state in any of the elements of the subset, with weight being the sum of all the product of all those weights. The sum of the sum of all those weights, where you take the residual times the final weight. Okay, I think I said that right. Okay. Again, there's a queue, so you can do this on the fly. Rather nice. Okay. All right, no more algorithms. We'll move on. Okay, so finally, there's some normalization operations, which, for instance, you can topologically sort a machine, you can sort the transitions, you can redistribute the weights in a way, this pushing, which arranges the weights. For instance, if you push over the log semi-ring, it'll arrange that the sum of all transitions, sum of the weights in all transitions leaving a state equal 1. In fact, the general definition is the sum of all weights in the semi-ring equals the 1 of the semi-ring. Epsilon normalization, which will put all the epsilons on the input side after the non-epsilons, which is sort of the closest you're going to get to an epsilon removal when you only have one side. Okay, and synchronization, which allows a certain. It's doing less work than epsilon normalization in some sense, but produces a certain well-defined relationship between the inputs and outputs, which is useful in some cases.
Mike, could you say a couple more words about the topological sort?
Sure, that's a classical algorithm that just arranges for an acyclic graph that the states are numbered in such a way that every transition proceeds from a lower numbered state to a higher numbered state. Okay?
Yep.
So why would you want to do that? Because search algorithms the acyclic search algorithm, which is a linear algorithm, wants to have the input topologically sorted. Okay. That's a classic reason to do it. And which brings us to this. And then some search operations. There's shortest path, which you give it away to Transducer, and it will give you the best or n best paths out. And so just to give the idea of complexity of what's going on, it will look at the machine, and so hidden details. Well, actually, each machine knows certain facts about itself, or may not. It may know that it's acyclic, in which case it'll immediately switch to the acyclic algorithm. Or if it knows it has positive weights, it'll immediately switch to Dijkstra. Or if it knows that it has, otherwise it'll use Bellman-Ford. These are all different algorithms for different cases. If it doesn't know these facts, it'll walk the machine to determine them. Okay, so these are hidden features. But as far as you know, you just call shortest path. On the other hand, if you're a control freak, you can, at least in the library, you can actually specify what you want. In fact, it's even crazier than that because each of those algorithms are really just different Q disciplines on a meta-algorithm. You can pass your own Q, which some people in here have actually been thinking about learning, or if I don't know if they're here, but I've been talking about learning Q disciplines for search. This is an interesting problem. Okay. Okay, so that's just an overview of the algorithms in the library. Now I want to talk about some, the timing's pretty good, about the library itself. So this is going to be a sort of combination of, sort of how to use it along with sort of what was done. And so first I'll just do the trivial thing to say how to input, build a transducer from scratch. From some specification, and there are several ways. One could do it from a textual file representation, and people who use the AT&T one will know this already because it's exactly the same. We kept compatibility. You can build it directly from code, so you can build it in code. And other methods which we don't have, either we don't have or we're not giving out yet. So we don't have a graphical user interface. It'd be kind of cool if you could just sort of, draw lines and do things in some cases. That might be interesting. We do internally have ways of converting regular expressions, context-free rules, and we're working on context-dependent rules. These are higher-level representations that we can compile into transducers. Eventually, we hope to offer these externally well under the Apache license, but that's not ready for prime time yet.
You have some bounds on eventually?
The story is they were written by one set of people who are not big open source. They don't care. So me or Cyril are going to have to go back and either convince these people they want to do it or do it ourselves. But I think it's going to be the latter. So it's sort of when we get around to it, I'm afraid, because we have other stuff to do. And it's, this stuff is fun, but you don't want to spend all your time writing code, right? So, okay. Or cleaning up somebody else's code, right? Okay, and part of the problem is that Google infrastructure has lots of peculiarities, and you've got to take all that out. All right. The textual format is very trivial. You have you specify a bunch of you specify an input state, a source state, a destination state, an input label, an output label, and a weight in a very trivial way. If it's a line with just two elements, it's the final state and its weight. The initial state is the first one. And this very dumb format is dumb, but it's easy to write scripts that generate them, so that's why we use it. And it's also, I can blame the people at AT&T, which is me, for why we use this format, because we want to be compatible. And you also need to specify, when you have symbolic labels, what their numeric representation is, because internally everything is represented as integers. And their operations.
Zero is still reserved.
Yes, exactly, right. Very similar operations AT&T for compiling these into a binary representation, which is used for everything else because that's efficient. You can print it out again. You can draw it. That's how these pictures were produced. Okay, and so here is how, once you've built one of these, if you want to read it into a C++ program. So an FST is a C++ class. It's templated on the arc or transition. We'll see why that's interesting later. Sort of very straightforward. You have a read operation to read it in, and you have a write operation to write it out. Okay. And here's the equivalent way to build the same picture I drew as C++ code. So you start by defining an FST, and we're going to use, so there are many, many different internal representations. You have very different kinds of FSTs. This is a particular one, a vector FST, which represents an FST as its states as a STL vector, and its arcs are an STL vector for each state. Very straightforward representation. It's templated on the arc, and we'll see what that means in a little bit. We could use something else here, something you wrote yourself, whatever you want, as long as you meet the interface, and we'll see that later. So we have, the interface says, oh, I have to, if I'm going to have a mutable FST, I want to have an operation which adds a state, allows me to assign the start state, allows me to add an arc at state 0, and here's the arc I'm adding, and here's a constructor for the arc, input label, output label, wait, next state. I set the final state, and I'm done. Okay. So what was this template argument? What this allows is you can use whatever you want as long as you meet certain properties. So for instance, you can use whatever you want for the label or the next state as long as it's an integral type at the moment. Okay? So if you want to put a short here, a car, because you want to save space, go for it. More interestingly, for the weight, this can be anything which meets the semi-ring properties, right? So here, the weight, I'm using tropical weight, which is built into the library. But if you choose to define your own, and it meets the properties, which are now nicely defined on the website, it's going to work. And even fancier, it will correctly do I/O and write file formats, and the binaries will work with them if you write dynamic shared objects and read them, or you compile it in. So it's all rather happy, and including changing the set. If the set were, a 4-tuple of floats, it's going to work if you do everything right. Okay, so what's an example of a very simple weight function? This is the tropical weight, which is, what did I have to define? This is, in some cases I'm simplifying this a bit, but you get the idea. So I'm going to, as I described earlier, you're going to need to define identity elements, the 0 and the 1. So in the case of tropical, the 0 is going to be a positive infinity, and the 1 is 0, if that's not confusing. Internally, it's going to store whatever it is as a float. And you're going to need to add a plus and a times as companion operations, which plus is min and times is plus. Okay. Now, one beautiful thing about this all compiles away into nothing. When you add two numbers, when you call times, it's actually doing the underlying plus of C++. Extremely efficient. And AT&T didn't do this, so you're getting much more efficiency here, right? Okay. But it's also very compositional in that you can not only can you define your own semi-rings, you can actually build up more complex ones from simple ones. So for instance, there's a template in the library, product weight. So if you have two semi-rings, the product, meaning the semi-ring over pairs from each of where the first component's from the first semi-ring and the second component's the second semi-ring, is a semi-ring, where the plus is the 0 is 0 from one, 0 the other, 1 is 1 from one, 1 the other, and the plus is done coordinate-wise. Okay? So if you just construct a template with where you provide the two component semi-rings, you get a new semi-ring. Now, why is this interesting? Let me give an example. We put all this machinery in there and wondered if people would use it. I found the speech people went off and wrote their own. So one problem people have had using, say, the AT&T one is, so how do we want to? We don't want to have just the, in speech, we don't have just the total weight on the speech lattice. We'd like to store a bunch of stuff. We'd like to have the grammar weight and the acoustic weight and the duration. Well, what they did is they store as their weight a 4-tuple. The first element is the grammar weight. The second element is the acoustic weight. And the last two elements are the duration. And why is it 2 elements? Because they're using the expectation semi-ring, which will keep track of the average duration. Cool. And it's all very efficient. And once you do something like that, you write it once, and everything works with it in principle, right? You can do shortest distance. You can compose with it. It's all happy. Okay, so going on a little bit further in the library, for the operations, they sort of come in 3 flavors. There are those operations which modify their input. There are those which create a new FST, and there are those which I described before are lazy. And in this library, they're distinguished basically by their function signature. So a destructive operation takes a pointer to an FST as its only argument and modifies it in place. Those which are constructive take an input and take a pointer output. And the lazy ones are new FSTs. By the way, the standard business is just a type diff shorthand for FST of standard arc. So wherever you see standard, it's just a convenience. You could write it the other way. Where standard arc is the tropical. But you can, if you wanted to read log, you would say FST. Actually, you could say log FST. But if you had your own type, it would be FST of your own semi-ring. Okay. So here's a simple example of using the library at the share level. Straightforward. You call this is doing application of a transduction, which is essentially you want to do composition followed by projection. To compose, one or both of the machines have to be sorted appropriately, sorted on the output for the first machine or sorted on the input for the second machine, because we have to do this matching and we're using binary search. We then call the project operation to just keep the output after we've done the composition, okay? And this can be done as a nice pipeline too, okay? So you don't have to, you can write it all together. In C++, it has there's a parallel. You read the machines in, you sort them, you create a place to put the output, which can be, in this case, we're using a standard FST, but you could create your own. If you have your own storage class that meets the properties, you can create it, you compose it, and you project it, okay? Now let's do some more interesting cases. Here we have the shortest distance operation, which from a given state computes the cost to getting to each state, okay? And that cost is put into this, this output vector, right? So in the forward algorithm, that would be, you're using the log semi-ring. In shortest path algorithm, you're going to be using the tropical semi-ring, right? But this can be generalized to many semi-rings. In fact, I'm showing here, we can call it with a tropical semi-ring. By the way, because of C++, this is overloaded. It just figures out what the right semi-ring is, right? So here I'm going to do it over the tropical. Here I'm doing it over the log. Here I'm doing it over the right string semi-ring. Okay, so this means I'm now going to get what's called string potentials at every state, which is useful for some algorithms. Now, if I call it on the left string semi-ring, that's not defined because the algorithm requires right distributivity. You get an error. Okay, and that's because when you create your own semi-ring, or we create ours, we give bits that say these properties hold. It's commutative. It's blah blah blah, and each algorithm will check to see what's going on, and hopefully it will give you a good error and won't let you do something stupid. Okay. So there's a sort of design choice when you're doing building a library like this, and one of them is, a key one is how you represent the outputs. And one way to represent the outputs, so each transition can, the input, in our way, we're representing the input and output is, on a single transition, is just a single input label or output label, or possibly epsilon. And that has some nice properties that it's symmetric, and it's very good for things like composition. And since I mentioned that's sort of the workhorse for all sort of, combination operations, we really want that to be efficient. So this is sort of our sort of standard way of representing a transducer. But another very convenient way of representing a transducer is to have the outputs be not just a single label, but a string. And in some sense, this is the more mathematical way of representing it. And its advantage is that there's some algorithms which very naturally want to treat the output labels as a weight. So for instance, I gave you the algorithm for weighted determinization. How do we do weighted transducer determinization or transducer determinization? It's by treating the outputs as weights, and we'll see that in a minute. And there are other algorithms, minimization, label pushing, epsilon normals, all want to have this representation. And if you looked inside of AT&T and saw what we did for this, it was just horrible. Basically, everything was special cased and a mess. What we kept in this library much closer to the math, and everything is sort of, well, I'll show you how we did it.
In the case time, then would that be sort of would that be your string semi-ring?
Exactly, right, right. So what we're doing here is we're now going to, so another way to say this is, I'm sorry, I should have said that. Another way of thinking of the outputs being strings is that now we have a new weight, which is the cross or the product between the strings, the left string semi-ring and the weights.
That's when you get the composition you look for the.
Right, and this is exactly the idea of how to do determinization, right? So in fact, that's what I'll show, right?
Assuming that the machine is not deterministic to begin with. I mean, if you have multiple outputs for one input.
Then you're in trouble, right. Well, all the same caveats, right? So it only works when it works. But that would be true whether you did it in a yucky way or you did it in a beautiful way, right? So here is now roughly what the code for weighted transducer determinization looks like. But this is hidden for you. If you call it, it works. But inside, you'll see essentially. So what's the key idea? We create a new semi-ring, which is the product between the string and the weight semi-ring, right? Now this is a little bit of a lie. There's two lies. One is this really should be templated on the weight because we don't have it to work just on the tropical. We want it to work on whatever weight we have. The second is actually internally we don't call it the composite weight. Internally, right now we're calling it for something of a joke. This is how we did it. Fernando and I did it here at AT&T. This is how Marriere had done it back in France. So we called this the American and French semi-rings. And so in the library, this is now called the Gallic weight. But that's a little bit of a joke. I don't know if we're going to stick with that. But in any event, I gave a talk about this in Europe recently, and I didn't want to go there with that. So I just called it the composite weight here. And so what's the idea? To do transducer determinization. So here's an operation I didn't have much time to talk about, but it is the idea here is map is essentially for any FST, you can define a function object, which you define yourself. It creates a new FST, in this case an on-the-fly FST, but there's versions for constructive and destructive that transforms that arc in some way. So in fact, invert and project are implemented by a little functor that flips the input and output in one case or projects. So you can very quickly write new algorithms by just where they're just simply mapping over the transitions, right? And in one case, that mapping is just to map from the string semi-ring to the from the American to the French, if you will, right? So there is a mapper for that. Once we've done that, we just call the weighted determinization. We then we just need to then map back. But there's one slight fly in the ointment, and that is at this point we might have a machine which has on the output a string of length greater than 1. And you can't just map back trivially. You're going to have to do something to distribute that string over individual transitions. And the naive thing to do would be to just generate new transitions. A better thing to do would be to have an algorithm that would recognize, oh, there's space on the next transition that is an epsilon. I can put it there so I don't have to create states. And there's an algorithm which generalizes that notion, which we call factoring weight, which will do just that. And furthermore, it's general enough that it can actually do other kinds of things too, like put prime factorizations of weights on things. But I don't want to go there. So essentially, you do this step to ensure that there's only one. The string in the output is a single label, and then you map back.
And
okay?
How does this interact with this idea of putting all the input epsilons at the end?
Different, not related.
Because you mentioned that you could put a symbol on its string if the next symbol.
Well, same thing. So if you
this is on the output side, I realize, but
so the problem is in the process of determinization, strings can appear on the output. That's where you're host. So it doesn't really pre-processing the machine isn't going to help you. I don't think so. But the operation for doing that epsilon normalization uses the same kinds of ideas, right? Okay, and so what more do I want to say about this? Just that minimization and label pushing and epsilon all make use of this idea. And furthermore, we're finding new uses. Having these lower level primitives, you can create new algorithms that you have by having these piece parts. And finally, let me give an example here of a semi-ring that's kind of fun can be added quite quickly to this library, and that's the expectation semi-ring, which I think Jason has talked about in his own work. I remember us using it back in the early 90s for trying to compute the entropy of language models and whatnot. And here's a more recent use in which we're using it to compute the cross entropy between two weighted automata. And it's basically a combination of generating this semi-ring, which you can verify yourself as a semi-ring, which will compute averages, and intersection, which is going to do essentially combining the models to do the cross entropy. I haven't really got time to go into it, but it's all actually pretty trivial stuff, and a shortest distance to sum them up. And by the way, that's being used in a more general setting in a kernel library, a string kernel library that's being put together for libsvm by Marriere and Cyril. Okay, and so better finish up here. It's just to say a little bit about the design of the FSTs and how on-the-fly works. We have an FST is basically just there's a base class which has just need to be able to say what the start state is, what the final weight is, and how to read it. And two additional companion iterators, something to iterate over the states and something to iterate over the arcs. Okay? And if you have those, so why do we do it this way, by the way? So if you, for instance, pass in here that the specific type of the FST, that it's a standard vector FST, iteration involves no function calls, it's just looking up the answer in these vectors, so it's extremely efficient. If you pass a more generic FST, where you don't know the type at compile time, it will do something somewhat less efficient. So you get both choices, which one you want. A subtype of the standard FST is a mutable FST, which adds the various operations for mutating the machine. You can define your own subtype that's a mutable FST if you want. It has an iterator as well. So now, just to summarize here, let me show two examples of how invert, which remember is just creating the inverse relation, can be written in each of these two ways, destructively and lazy. So in the destructive case, it's trivial, right? We iterate over the states, we iterate over the arcs, we extract the input and output label, we flip them, and we set the arc. Very simple, right? Lazy is a little more interesting. So remember when I said by lazy, it's only doing the work it has to as you ask for it. And so in this case, you create a new FST called invert FST, which derived from the base class FST. And essentially it forwards everything. The start state of the output is the start state of the input. The only thing that's different is the arc iterator, the value of the arc iterator. And when you actually go to request what's the transition, it's then at that time it's going to flip them and return it. But before that, it hasn't done any work and doesn't use any storage, right?
Couldn't you generically make a lazy version of math FST?
There is. I showed it. Yeah, in fact, that's how this is done. In fact, invert is exactly written as a lazy version. It's just a functor, right?
Yes.
Right. So I use this as purely for illustration. In fact, composition you can't, and composition is much more interesting here because now you have to write, or determinization, because you have to write. So start in composition returns a new state, which takes the two states from the initial states from each of the two machines, hashes it, and returns a new state. And composition, transition level, it's going to be generating new transitions as you go. But I gave this because it was a trivial example. And let me just sum up, good time here, with future directions here. One is, I already mentioned, we're thinking about providing regular expressions, context-free rules. Brian Rourke has started work with Cyril on a n-gram language modeling package. And to my knowledge, this will be the first open source version. Is that right? That's what I believe. I mentioned the string kernel learning work. And then there's a lot of work, really, there's an awful lot of open problems and algorithms associated with this library. Let me just mention three. One is how to efficiently do string matching, which involves sort of dealing with n-way composition. So where you have two strings, for instance, and some sort of something that determines the cost between them. That's work Marianne and Cyril are doing in parallel with their working on the string kernels because they need it, because essentially that's the string kernel computation. Another one, which is near and dear to me, is this generalized composition filter, because I think the single biggest complaint we've had of using our approach for speech recognition is that you have to compose if you're building a big transducer which maps from context-dependent units to words, and you want to use that as your recognition transducer, you have to undergo various optimization, composition, and determinization steps. And the result is beautiful and nice and small, usually. Getting there involves lots of computation and lots of memory. In fact, if you want to do it for a very large, say, broadcast news language model, you might need 4, 6, 8 gigabytes. And not everybody has that, and they complain. This is just to build it, then you have a nice result. So the problem is that essentially determinization uses a lot of memory, and one easy answer to that would be, oh, wait, if I just determinize the components, the lexicon and the grammar, for instance, the composition of two deterministic machines is deterministic. Why don't we just predeterminize, determine ahead of time and then compose them? The answer is the current composition algorithms would create huge numbers of non-coaccessible paths, dead ends, if you will, and be a disaster. But there's no inherent reason that that's the case. We're exploring algorithms that will recognize these dead ends and eliminate them. There actually has been a fair amount of work of special versions of this. For instance, Diamantino has done something for building explicitly when you have a lexicon and a language model that it works. And there's been other work where people are doing sort of inefficiently, I believe, DFSs and things like that. But we're looking at sort of both efficient algorithms and general algorithms, and we think we have something to report in the near future. Another area of interest is dealing with all kinds of ways of matching. So I mentioned already the epsilon transition, which has the property that it's a free move and it matches everything. But there are other symbols that you would care about that would be very useful. For instance, you might have a sigma symbol, which matches everything, but you consume a symbol when you take it, right? Sigma matches it's basically star, right, in grep. Two other useful operations would be phi and rho, where rho is rest, right? So this would say, if I can't match anything else, I'm going to take rho, rest, or phi, which says, if I can't take anything else, I'm going to fail and take this transition, but not consume anything. So for instance, phi is the very natural transition for a back-off language model, instead of using what many people do now is epsilon. And this is actually, all these are in our library at the moment, but only this is documented, if you will, because the semantics of these are fuzzy at best. And so we're looking at trying to make this much more beautiful and actually have algorithms. So epsilons are correctly dealt with in the library and in the algorithms, and that you compose two things and epsilons appear in the output. The only way we know now of dealing with these symbols is to immediately expand them. And so you sort of lose the benefit of using them. But if we had ideas of building algorithms that treated things like these in a clever way, so that the output is now both compact and correctly keeps the semantics of these labels, it would be quite interesting. And we have some ideas on how to do that. Okay. Any questions?
First, the immediate question on the last slide. If you consume them, does it carry through with things like composition? Wouldn't you have to know what you consume?
So I'm sorry, which case?
So if you're using this consumption symbol.
So these are in composition only as hidden features where you pass a composition an argument that says, I have this symbol, and what it does, it immediately expands it before the composition is done, if you will.
Okay.
All right? Conceptually. Right. Same with, so for instance, difference is implemented with rho, or complement. Right? Because the way you complement an automaton is if it's deterministic, you need to first complete it, which means at every state you have to be able to read every transition. And so you create a new state which every transition you can't read goes to, but you don't want to put a million transitions, you put the rest simple. And then you just flip the initial and finals, the final and non-final states. Okay? But that's handled by composition cleverly knowing if it can't match anything just to follow rho. But it's not treating it, rho doesn't appear in the output, it's expanded it. That's what's not good. So you would like to have some way that you could have phi in the language model, and you compose with the lexicon, and the output is both compact and phis appear in the output, or something like phis.
Did I read your code correctly that you need your weight classes to be able to convert to floats and vice versa?
No, that's only true of for that particular. That's a convenience for that particular class, but no. Yeah, I mean, I initially didn't have that, and people were griping that they had to, put it, There's an example here. They were griping they had to put here tropical weight of 0.05, so we put in a converter, right? So it's just a convenience. But normally you would have to, if you want to construct an arbitrary arc, you would give the input label, the output label, and the weight, and this would have to be of the right type. This is a float, not a tropical weight. But
right.
there's a constructor that takes the float. So it's just a convenience.
Right. Okay. And the composite weight guy had conversion going the other direction.
It did? I don't see it.
No, the
Oh,
composite
sorry.
weight guy. Yeah, there. So
Which one?
his initializer list is initializing these floats from the two weight arguments. This is this typo I've had a long time. This should say W1 and W2. I kind of wondered about that.
No, I keep seeing the typo and keep forgetting to correct it. Sorry,
Okay.
this should say W1 and W2.
Okay, yes.
Sorry. Yes.
So the rows and phis that you had on the last slide reminded me of some work that was done a number of years ago, probably by Gardeman and Van Noort, where arcs were labeled not with alphabet symbols at all, but with predicates over a possibly infinite alphabet. how hard would it be to support that kind of thing?
So, all right, so,
I mean, it
so,
might be-
so
it might
let
be
me
useful
mention
for
the,
speech,
the ideas
for example,
we're thinking of. One is to treat. So one person asked, why can't we represent? They wanted for their application, which is OCR, to represent intervals. So
Represent, sorry,
intervals, saying, you know, I want to have A through Z, basically, you know, or, right, so if they're using Unicode, so they have huge ranges. And then they said, oh, well, why can't I have consuming and non-consuming intervals? And if you go to something like that, I think you can actually make the semantics all work out. But I would much prefer to, instead of having that sort of hardwired in, to instead, back up here. That's sort of where we're thinking about now is, let me say here. This now has to be an integral type. Let's instead abstract we've already given saying that a weight is some semi-ring. What is the best abstraction we can have over a label?
Yes.
That still makes everything work.
That's
And we don't know the answer to that yet. So, but I mean, for the longest time we thought the answer was it has to be the free monoid and there's nothing else you can do. But so it's basically integers, if you will. You know, and
I don't think that's true.
we can talk later about it.
Yeah.
But yeah, I don't think it's true either. So, but the question is, now it becomes a question of what's the right algebra to create for this, and how do you? So it's something interesting to follow.
If you do it right, you can have continuous quantities as your output labels, which means that you could just read speech signal directly and match it against a transducer. So in order to do that properly, you need you need to be able to say that your arc actually represents in a possibly infinite set of pairs of let's say triples of input, output, and weight. And once you've done that,
So I'm sorry. What's your set?
Sorry.
What's your set? Label set?
So your set is 39-dimensional vectors.
And what's your times and plus? Or what's your what are your
No,
operations?
the weights. The
No,
weights
sorry,
are usual weights.
what are your operations?
Yeah, so you need to be able to
What's your
do
concatenation?
union and intersection, I think, on these sets, and maybe reorganize in some way. I mean, basically you're operating with functions rather than with individual points along that function. Anyway, we can talk about it, but I think that the work has actually been published by others, not necessarily for the weighted case, maybe just for unweighted automata. But you can imagine what you do if you have an arc labeled with in some predicate, and let's just say to make it easy, A through Z, and something else, some other interval. Then when you intersect those arcs, and when you compare to see if you match, you say they match, but what you get, the arc is now constrained to the intersection of those
That's
intervals.
exactly what we're thinking.
And if
Right.
the intersection
Exactly
is empty, it
what
doesn't
we're
exist.
thinking, right. Exactly. And then what's the most general case of that, right? Is it some sort of a lattice or something like that? I don't know.
No, I think it's a user-defined class.
But there's got to be some algebra. You can't just do anything.
Yeah, it's a lattice, sure. That's right. But it gets a little more complicated once you want the weight to covary with the symbol, which is what you'd want if you wanted to be able to read the entire Gaussian, for example, corresponding to a particular phoneme.
So in the case of these intervals, though, it could also, as I say, we imagine both consuming and non-consuming intervals, for instance.
Mm-hmm.
So you have non-consuming symbols, and then I think you want that to work correctly with the composition algorithm, et cetera, et cetera. It's sort of interesting.
Yeah, no, it's an interesting challenge you got to work out. That's right.
You need to get, basically, the matching things are composition and determinization. You get those right, everything else is going to work. Because nothing else cares about the labels. Okay. Any other questions? So, by the way, if folks are interested in using this and have questions, email me. First, read the documentation. Then email me.
You did very well. You had only 42 slots. The last time we did a 1 hour talk, you had 9 slots. I learned.
Thanks.